Chapter 2.4 is going to bring us into an exploration of parent functions and their transformations, okay? So transformations and parent functions should be things that you've started learning in Algebra 1, and all of these 8 parent functions that are on this front page of the notes should be functions that you're already familiar with. The first one's just linear functions, where f of x equals x, quadratics, where f of x equals x squared, they make parabolas, cubic functions, where f of x equals x cubed, square root functions, where f of x is the square root of x. Remember, they go like this. They have the domain that ends because you can't have negatives under the square root sign. You have exponential functions, which are e to the x, okay? You have natural log functions. So the natural log of x, remember that's what ln stands for, is natural log, and they go this way. You have reciprocal functions. Remember, these can also be called rationals. Okay, so they're also called rational functions. Usually I'll refer to them as rationals, so that is what we're talking about for this one, where you've got a number over the variable. They always have an asymptote, okay? And then the absolute value function, which always makes a v. So these are the 8 functions that you should be able to see an equation that's written in this form and automatically know the general shape of the graph, okay? So for something like example 1, what they're gonna ask you to do is they're gonna ask you to recognize each of these different pieces and know what the basic shape of the graph is so that you could graph this fairly easily without having too much trouble, okay? So if we were gonna graph this piecewise function, and remember a piecewise function is just different pieces of a function that hopefully connect together. So if we were gonna graph this, and they want us to just sketch it, and I'm gonna sketch it using the parent functions that they gave me up at the top. So I know we're going from less than -1, so let's go like -2. And we're only going to +1, so we'll just kind of graph it like so. And it'll look something like this, okay? I guess I could have drawn that y-axis a little straighter, but it's a sketch, so we're okay. So this function, g of x, is the linear parent function, so it is a line, so it's gonna match this function, it's gonna match the linear function everywhere that x is less than or equal to -1. Well, the whole purpose of a linear function is if I plug in this number, the output is going to equal the input. So if I was at -1, I will also be at -1 here, okay? So -1 on the y, -1 on the x, that's linear. This has an or equal to sign, so that means it gets a filled in circle. And I know that this is a line that goes at the diagonal. So that piece should look something like that because it is linear, okay? So linear. This piece of the function, since it's x squared, is quadratic, okay? And we're going from -1 to 0, both with open circles, okay? And I know it's a parabola, so if I were to plug -1 in, I would get +1. And if I were to plug in 0, I would get 0. But since I know it's a parabola, I know it's gonna be a curve, and I'm not gonna draw a straight line, okay? So even though it's a sketch, I know that this graph is supposed to be curved, so I'm not gonna draw it as if it were a straight line, okay? The next piece of the graph is a square root function. Square root, okay? And that's from 0 to 1, and it's got the or equal to sign on the 0, so on the 0, we're gonna get a closed circle. If I plug 0 in, I know that this is gonna be 0, so that makes this open circle now closed. And I know that if I plug in 1, I get 1, and it's an open circle. And I know that it's the square root function, which remember the square root function, that's probably one you're not as familiar with, but remember square root functions look like this. So this function should look something like this. And then go up forever, except that it stops at our boundary of 1, okay? So if we're greater than 1, x to the -1. Well, remember that -1 just means it's on the wrong side. So this x to the -1, it's on the wrong side of the fraction bar. So it's really this. So this is the reciprocal function or rational. Either one of those is correct. But that function, greater than 1. So if I plugged in 1 here, I would get 1, which is an open circle. So that's here. And if I look back at my rational function, it looks like this. So remember, it's coming in this way, right? Just like it is right here, because at 1, we're right here, so it's coming in. So it's the rest of this function. So it would be coming in, but that's not part of the boundary. and then it picks up where it left off, and it gets closer and closer and closer to 0, but it doesn't ever actually cross because it does have a horizontal asymptote. So this is the graph of this piecewise function, and it's pieces of all of these parent functions, okay? So now they want me to check for domain, range, continuity, and relative extrema and symmetry, okay? So let's do them in order. So let's check the domain. So the domain of this function, it exists everywhere over here, it exists right here, it exists here, but it does not exist at 1 because it's an open circle. So I'm going to write that as x cannot equal 1, okay? And remember, again, you could also do this. Either of those two answers would be correct, okay? Let's look at the range of the function. The lowest part of the function is going to go on forever, so this function goes from negative infinity, and then it goes up. It does not exist between -1 and 0. Oops. It exists at -1, but then does not exist between -1 and 0. So we need to pick it back up, not at -1, but we need to pick it back up at 0. So it goes from negative infinity to -1, and then from 0 to 1. But if you'll notice at 1, we have 2 open circles, so it doesn't really exist there. So the range goes from negative infinity to -1, then there's a gap between -1 and 0, then it exists at 0, but at 1, we've got open circles. So it should look something like that for the range. All right, continuity. Remember, for continuity, we're looking for, does the limit exist from both sides? And we're looking, does the point exist there? And does the point equal the limit? So all of these places are the same. All of these work. This is continuous until we get to here. And then you'll notice as I come in from the left and as I come in from the right at -1, I get 2 different answers. So this function is discontinuous. So continuity, we're going to have a discontinuity. What kind is it? Let's see. It is a jump. So a non-removable jump discontinuity at x equals -1, okay? At 0, we're fine. At 1, though, we have a hole. So at 1, we have a removable point discontinuity at x equals 1. And it's continuous everywhere else, okay? Relative extrema. Remember, relative extrema occur where we're changing from increasing to decreasing. So extrema. So on the leftmost side, we don't have a lowest most point. This can't be an extrema because it doesn't change increasing to decreasing on the other side because it stops. The same thing with this one. But this 0, it goes from decreasing to increasing, so it has a relative minimum at x equals 0. And right here at 1, it would have a relative maximum, but because there's a hole, you can't include that as a relative maximum. So the only relative extrema this has is the relative minimum right here, okay? And then our last thing is symmetry. And I'm not going to plug any equations or plug in the -x and go to that trouble when I have a graph, because I can just look at it. So if I look at this graph, if I cover up this side, this piece over here, is it exactly the same as what's under my hand? Well, no, it's not. So it's not even, okay? The other thing that we could test is it symmetric about the origin? So do all of the things that exist here exist in the opposite quadrant? Well, I have a line here and I don't have a line in that quadrant. So there is no symmetry to this function.